And today it's a pleasure for me to introduce Professor Gina Lorenz. Professor Lorenz received a PhD from University of Colorado Boulder. After working at the University of Oxford and University of Delaware, she joined the department here in 2015. Her group conducts cutting-edge research in ultra-fast quantum optics and optical magnetometry, and develops tools for the next quantum revolution that she's going to tell us. Let's welcome Professor Lorenz.
All right, can everyone hear me well in the back? No? I'm going to increase the gain here. It's okay? Now is it better? Okay, great. Good morning, everyone. Thank you for the introduction. It's great to be with you this morning to talk about humankind's evolution towards a quantum internet. And this is a really exciting topic. It's something that I'm studying in my lab. The person who introduced the lab escape, as he mentioned, he is an expert in this area. So let me start by asking, what is the internet? Any comments on what you think the internet is? Yes? It's a bunch of computers connected, yeah. Anyone else? Yes? Data transference. Great. Any others? Yes?
It's the network of networks.
It's the network of networks. Okay, nice. Well, you all are really close, but technically, the internet is where you get cute cat videos. Yeah, sorry. So now, it's interesting, now that you know what the internet really is, let me talk a little bit about the history that connects us with the internet here at Urbana-Champaign. So back in the 90s, an Illinois student, Mark Andreessen, landed a job as a student programmer here on campus at the National Center for Supercomputing Applications. And there he teamed with his staff member, and together they created Mosaic, which was the first graphical web browser. This is the way we access the web. It makes it very easy to find information on the web. Soon after graduating, he joined Jim Clark in Silicon Valley and started a new company and founded Netscape, which was one of the most dominant web browsers for a few years at the very beginning. So that's an interesting connection with us and the internet. And yeah, actually, you guys are all right. The internet is a global communications network consisting of thousands of networks, typically interconnected by fiber optic cabling. So actually, that's a technical term there. That's the first thing I'm going to talk about that's very related to the quantum internet. The same fiber optic cabling that we use to transmit information today can be used to transfer quantum information in the future. So what is that fiber optic cabling? And I'm just going to have to switch over here. OK, so fiber optic cabling is comprised of glass. And let's just think about what happens with light when it interacts at an interface. So I'm going to make one interface air and the other interface glass. Okay? So currently, when we send information over the internet, it's in the form of light that is encoded with information. And that light is created from a laser. So if you think about what happens when a laser shines from air to glass, it's pretty intuitive. The light is partially transmitted, partially reflected. And as we vary the angle of incidence, we all have this reflection and transmission also vary their angles. Now, the way a fiber optic cable works is the laser is actually launched inside the glass instead of inside the fiber. So I'm going to switch places here. We're going to go from glass to air. And so we launch a laser inside the fiber glass. And now look what happens. As I change the angle of incidence of the laser on this interface, it goes from being transmitted and being reflected to only being reflected at some angle. This is called total internal reflection, and it's the basis of how we transmit light in fiber optic cables. Imagine you have another interface at the top with air, then the light will bounce back and forth inside the glass, never leaving the glass. And so these fiber optic cables are these thin threads of glass that the light is trapped inside and propagates along, carrying the information from one place to another. All right, so that's fiber optic cables. And this is an image of a bunch of cables. You can see the light coming out. And this technology is still going to be used in our quantum internet. Again, we're going to use light, but it's a very special type of light. Okay, here's an image of the internet that was obtained illegally by someone pinging everyone's computers at once. You can actually see the usage over the course of a day. The shadow of the sun is kind of shown moving across. It's very faint in this image. And you can see the usage go up and down depending on what time of day it is. So let's think about what comprises this internet. Well, we have ourselves sitting at home or in the lab, and we have some information. And that's represented by this piece of paper that has something written on it. And we want to then send this information across the network. So that's where the fiber optic cables come in. So from where you're sitting, you can then send information via light along the fiber optic cable. And then to make sure it goes where it needs to go, there are some switches that make sure it goes in the right direction. And if you want to send it over a really long distance across the world, what happens is the light does eventually fade. It eventually starts to be leaked out of the fiber. So you need some kind of stages called repeaters that allow you to re-amplify the light. Make sure it goes a longer distance. And this allows you to go around the world and reach users all around the world. Okay, so these are the components of the internet. And just like the internet we have today, the quantum internet of the future is going to have similar components. The fiber optics can be the same, but these components will be different. And that's what I'm going to talk about today. So a lot of what I'm talking about is discussed in detail in this really nice paper that was just published this month, so very, very up to date. It's called The Quantum Internet, A Vision for the Road Ahead. And so if you're interested, you can look this up on your own and learn in very much detail. Okay, so first let's talk about why do we need a quantum internet to begin with? Well, the purpose of a quantum internet is to enable applications that are fundamentally out of reach for the classical internet. So what are these desirable applications? Well, one is secure communication. So we can have absolutely secure communication using a quantum internet. We don't have to worry about eavesdroppers, hacking, and all those issues. We also eventually will have secure access to remote quantum computers once those come online. Quantum computers allow us to solve very difficult problems that are impossible to solve with a classical computer. And it could lead to new discoveries like new quantum chemicals that allow, so doing quantum chemistry, we can come up with new drugs. It allows more accurate clock synchronization, which in turn improves our GPS. And then finally, it has scientific applications. Specifically, there's one I'm going to talk about that combines light from different telescopes to improve astronomical observations. So it's actually, I'm going to focus on the red and the blue candies here. So secure communication and this application for astronomy in my talk. And that's red and blue. That actually reminds me, I need to make sure you all are on board with me. So before I go any further.
This is your last chance. After this, there is no turning back. You take the blue pill, the story ends. You wake up in your bed and believe whatever you want. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes. Remember, all I'm offering is the truth, nothing more.
All right. Okay, so I just have to ask you, what are you going to do? Now's your last chance. Remember, all I'm offering is the truth. You can either wake up tomorrow in your bed, believe whatever you like about quantum, or you can take the red pill, and I'll show you down the rabbit hole. So if you want to leave, go ahead and leave now. All right, so I think we're all on board for this. And let's go into the quantum realm. We're going to start where we are today. This is kind of representing what's being sent over the internet now. It's bits of ones and zeros that encode our information. And these bits, they can either be 1 or 0. I mean, that's what we're showing here. Now, the first strange thing about the quantum realm is that a bit that carries quantum information, or a qubit, it can be 0 and 1 at the same time. Okay, so what does it mean to be 0 and 1 at the same time? To explain this, I'm going to take you back in history to the first experiment that looked into kind of these strange quantum properties without knowing about the properties of quantum objects ahead of time. So we're going to go back to an experiment done in 1801 that wasn't fully explained until the 1920s. Okay, we're going to start in the real world, our everyday experience, and just think about what we'd expect to happen. Let's say there's this wall, we're looking down on the wall, and there's a gap in the wall, so there's a vertical slit. And we have a tennis ball, and we're going to throw the tennis ball at the wall, and sometimes it's going to go through that slit. And every time it does, and it hits that screen in the back there, we're going to mark on the screen where it hit. Okay, and we're going to do this over and over and over again, and it might, go straight through, it might hit at angles. Let's see what happens. Okay, so here we go, throwing the ball. I'm only showing the ones that make it all the way through, and then we're just marking where they hit the screen. And over time, you're going to develop a sense of, kind of the range over which you're going to hit the screen. And that's represented by the green bar there. Okay, so that's what we'd expect to see in our everyday life. Now let's make it a little bit more complicated. I'm going to add a second gap. So now there's a second opening in the wall, and I'm going to again throw the ball, and sometimes it will go through the path 1, sometimes it'll go through path 2. And we'll end up with 2 stripes. That seems intuitive, right? Does everyone agree with that? Yeah, all right. So now let's consider a different thing other than a tennis ball. A tennis ball is a very localized object, and you can hold it in your hand. What if it's very delocalized, something that's spread out like a water wave? Let's send a wave of water to this wall that has 2 openings in it. And these little bars here represent kind of the peaks and the troughs of the water wave. So blue is high and then black is low. So now let's think about, okay, what is the pattern on the wall going to be if we draw the highest points and the lowest points of the wave when it hits the screen? So just think about that for a moment. Just think about what you'd expect. And now I'm going to show you what happens. So what happens is you get this interesting interference pattern of kind of these high peaks in the middle, low peaks that are represented by white on either side, another high peak, a low peak, another high peak. And it's pretty easy to see how this happens if you just watch a movie. So I'm just going to show you what actually happens here. And just have to get it up. There we go. Okay, so this is showing if you were to drop something into a pond, it would create these high and low peaks and valleys. Those go through the double slits, and it's as if there's a new source for waves coming from those slits, as if you put 2 pebbles on those slits, and you end up getting interference of the waves. Okay, so let me just pause it right there. So in the center, you have a peak. That's like a maximum in the wave, and then you have a minima on either side, and maxima and minima and maxima. And it all happens in a way that we're very familiar with just from throwing rocks on ponds and that sort of thing. So again, this is quite familiar to us. There's nothing strange about this. Okay, so now let's consider what the actual experiment was. In this experiment, the scientists sent some light onto a wall with 2 slits. And these slits are very close together and very small. And what he found was really interesting. So when he sent the light onto these two slits, he ended, the question is, do you expect to see an interference pattern like the water? Or would it be more like a tennis ball? And this is what he found. He found it's more like water, which means that light is acting like a wave. Okay, so this was the first insight that light is a wave. Now, it turned out, though, that you can do this experiment where you can actually detect which path the light is going through. Yes?
Was he observing the experiment? What was happening?
Yeah, so that's a great question. Yes, so when we say observe, we mean figure out, okay, well, the light needs to choose, right? It needs to go through path one, path two. Let's actually figure out which one it goes through. Okay, so we have an observer. That's a great question. Someone who can see definitely which path it takes. What's interesting now is it always chooses one or the other. So you can do this over and over again. And what you find is that when you make an observation of which path the photon takes, it only always chooses one. There's no interference. It doesn't look like the interference that water made. It looks more like the pattern that a tennis ball made, a particle, something small and localized. So what's going on here? This is the weirdness of quantum mechanics. Light behaves both like a wave and like a particle, depending on whether you make observations of it. Okay? And this kind of phenomenon happens at a scale where we're talking about, single particles of light. So first, let me.
What constitutes an observation?
Yeah.
What constitutes an observation?
Yes.
What if that was a fly instead of a human watching it?
Yeah, these are fundamental questions, and I don't think we have them resolved yet, but yes, you need an observer. So what does that mean? That's a deeper question. So let's talk about what we mean by light is a wave. So light is an oscillating electric and magnetic field that oscillates in time and space, and thus like water waves, light can interfere. And that's what led to that interference pattern from the two slits. But light is also made of particles. Does anyone know who realized that light is made of particles in 1905? Anyone? Einstein. Great, you all are on top of things. So he received the Nobel Prize in 1921 for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect, which showed that light is made of particles. Anyone know what these particles of light are called? Photons. Great. So photons are our quantum objects here. Okay. So important point is, even if you just have one photon, if you do that experiment again, it will interfere with itself. This strange property can be shown not only in terms of two possible physical pathways, but any kind of property of the photon. So, for example, electromagnetic waves can have polarization, which means that if the electric field oscillates up and down, we say that the photon is vertically polarized. And if the electric field oscillates back and forth horizontally, then it's horizontally polarized. And you can think of these two possible states of the photon in terms of the path 1 and path 2. Path 1 is the photon is vertically polarized. Path 2 is the photon is horizontally polarized. And what physicists realized and built up as a theory is that in order for the photon to be able to act both like a wave and like a particle, there has to be something called superposition, which means it can be two states at once. It can be in path 1 and in path 2 at the same time. So path 1 here is represented by vertical, path 2 is represented by horizontal. In addition, if we make a measurement, it will only be in one of those states. Okay, another interesting property that arises out of this theory is entanglement. The idea here is you can have one photon that's in this superposition between two states. If you have two photons, both of which can be in superpositions, you can entangle them such that knowing about one tells you about the other. So this is what an entangled state would look like. If I check the green photon and find it vertical, it will end up causing the red photon also to be vertical. If I measure the green photon and find it to be horizontal, the red photon also will be horizontal. They are entangled with each other. Actually, what's interesting is here at UIUC, we have a professor who was one of the first to demonstrate a polarization entangled photon source. This is actually a real photograph of what he created. So we have photons of different colors, and where the green circles meet, if you collect photons from these spots, they will be entangled in this state of vertical, vertical, plus horizontal, horizontal. And this person, I hope he won't forget, is Paul Kwiat, who introduced our lab escape today. So yeah, this was back in 1990. And so yeah, this is a very commonly used tool as we develop the quantum internet. And on that note, I really encourage you to go to Lab Escape. It's a lot of fun, and there's a lot of quantum physics in it that you can kind of learn as you go. And OK, so let's go back and think about how this resource of entanglement and photons create the quantum internet. So we know that these things are fiber optic cables that carry light. And what I just showed you is the kind of information you can create at your station. Okay, the kind of information you want to send. It can be entangled photons. These entangled photons go along the fiber optic links, and they convey information between users. So how would it actually look like? I mean, I gave you some kind of cartoony images of what it would look like. But in reality, you know, if you hold one of these entangled sources in your hand, what would it look like? Well, eventually, they're going to be very similar to a computer chip. On the left, I have a Raspberry Pi. And on the right, I have one of the most recent demonstrations of an on-chip source of entangled photons. So on the left, we have wires here that allow us to transmit information and change information. And actually, we have very similar things here. These are kind of like wires, except they're waveguides for light. So they're like the fiber optic cables that I showed. And they're carrying the light around. Then we have processors that allow you to create the information that you want to create. And that's similar to what's happening over here. You're creating entangled photons here. And then you have some way to transmit that information out to the internet. And that's what these over here are. These allow you to launch the light off of the chip into a fiber optic cable. You can see here the kind of scale we're talking about is similar. And so, yeah, so that's how it looks like today, but that's not the whole story. That's just part of the experiment that showed entangled photon generation. The rest of the experiment is shown here on the left. This is an optics table. The spacing between the holes is an inch. This is a student, one of the graduate students in my group, working on an optics table. You can see the scale. These knobs have to be turned to align the fibers to get the light off the chip. And then in order to characterize the chip, you have various components, some large equipment. It's all done in a large lab. So things haven't really scaled down in the same way that computers have. You still need users. You still need graduate students working in a dark lab. and we're still figuring out how to make the optimal type of photon source. OK, so that's images of it. What does it actually look like to work in the lab? Is it something like this? So the particles definitely get to enjoy such a world. The particles that we're dealing with, the photons, they are experiencing the quantum physics that I showed you, these strange properties. We don't join them in that area. We have to just work in the lab turning knobs. And so this is more like what our work looks like. And this was a video that was made at Oxford while I was there. It's supported by the Qubit Applications Project, which is funding for quantum information. So this is a story of Dr. DiVincenzo. DiVincenzo actually wrote the properties that we need in a quantum computer. But let me just skip to another part of the movie that shows what a lab looks like. Okay, let's see, play that. So you can see in the background here we have these curtains. Curtains are really important in labs that study this sort of thing. We need them to block the light and protect our detectors. So quite often we are working in the dark. Let's see what else we can see here.
This is Professor Kelly's flagship. This is a superconducting impact array, and these are the qubits themselves.
Let's see if I can skip here.
Becomes very visible.
And what do you hope to achieve with such a device?
Well, quantum particles exist in different places at the same time. So a quantum computer will enable you to perform hundreds or even millions of calculations at the same time.
So yeah, we also have very smart people in the lab, so that's good. And what you can see behind her are shelves with wires coming down, and those wires are controlling the various optics on the table that I showed in the photo earlier. All right, so let's see here. Okay, so there's an example of what an optics lab might look like. And now let's talk about how you can use these photons that are being created for new applications that you can't do using classical computers, using computers today. And the first concept I'm going to show you is spooky action at a distance. That's what Einstein called it when he first made this thought experiment. The idea is that you have a source of entangled photons. Okay, it's represented as a heart here. And we're going to send one photon to Alice and one photon to Bob. They want to communicate with each other. We're sending them over this fiber optic link. So Alice and Bob can be quite distant from each other, which means the photons end up quite distant from each other. And when Alice opens up her box and she can see her photon, and Bob opens up his box, they can then randomly choose how they want to measure the polarization of their photon. Now remember, these are entangled photons, so measuring the polarization of one affects the polarization of the other. So they randomly choose how to make that measurement. And then at the end of the day, they compare with each other and they realize that the results of their measurements are correlated. So you'll notice that the ones in red here, these represent the cases where they chose the same method of measuring their polarization. And those are all the same. And that's because the photons, even though they're far apart, are still entangled. So you can transmit information using entanglement at long distance. So let's talk in more detail about this process and what can you actually use it for. These are just a string of numbers. So it's pretty easy to motivate this part. If you look at the news, there's always something going on with hackers, vulnerabilities of encrypted messages. And the issue today is that if Alice and Bob want to send a message, let's just say Alice is at Everett Lab, Bob is at Loomis Lab on campus here. The way they would do it today is through using large numbers. They would take two large numbers, multiply them, and use this to create keys that can encrypt information. So one can encrypt it. and decrypt information after it's being sent along a fiber optic cable. So the issue is that if there's someone interested in getting that message, the only thing keeping them from doing so is the computational difficulty of figuring out what those two big numbers were that you started with. It's only a computational problem, which means if they have a large enough, more powerful enough computer, they can eventually figure it out and get that message. Of course, today, a lot of the news is around societal issues, like people putting in back doors and loopholes. But what I'm pointing out here is a fundamental issue, that even if you tried your hardest, this is still breakable. So this is where using entangled photons comes in. This is called quantum key distribution. Using this process, we're going to make a key that doesn't rely on multiplying large numbers, but rather creates a key secretly. So how does that work? Well, we have a pair of photons here. We're going to send one to Alice and the other to Bob. And they're going to choose randomly how they measure the polarization of the photon. And they're going to do this over and over again for a series of them. And at the end, they'll compare how they made the measurement without telling each other what the results were. They'll then take a subset of the ones where they use the same type of measurement and see if their results for those agree. And if they don't, they can then say, someone's listening in. How can they say that? Well, that person that's listening in, it's like the eye looking at which path the photon took. By checking, they change the state of the photon. It's no longer in a superposition. It doesn't create waves, right? It doesn't create a wave interference pattern. What that means is that it will choose. The photon will either be one or the other. It will no longer be a combination. And the way it makes that is 50-50. Also, the way the person measures it might be different than the method chosen by Alice and Bob. And so the chances that they get it right and send on the photon in what they think the state should be is lower than if Alice and Bob had perfect, if they measured it and found perfect agreement. There's going to be some error. They're not going to be able to send exactly what they need to send to trick Alice and Bob into thinking they're not there. And that is the fundamental thing that makes quantum key distribution secure. It's guaranteed by the laws of quantum physics. As long as quantum physics is true, you can say that this is a completely secure link. If Alice and Bob figure that someone's there, they throw away that information, although those bits, they start new until they know that there's no eavesdropper. And then they use that key to encode their information, which is now unbreakable. And they send that across the transmission line. So that's one big application of the quantum internet, completely secure communication. Now, what's the status of this? Well, actually, you can go out and buy a QKD server. You can go out and buy a source of photons that allows you to do this kind of secure communication already. So banks use it, governments can use it. Anyone who wants to keep a secret can buy one of these and use it. So where's the research? The research comes in because you can only use it over tens of kilometers. The fiber optic cable isn't perfect. You end up losing the photons. So you need some way to have kind of a repeater station for quantum information, just like you had a repeater station for classical information. Unlike in classical information, you can't just amplify your information. You can't boost it up because you can't copy a quantum state. It's a fundamental principle of quantum mechanics. You can't perfectly copy a quantum state. You'll always add some noise. That's also why quantum objects like photons are secure. You can't copy them. So so there's a different way to get around this. And it's called quantum repeater. Okay? The idea is that you take a longer distance and you split it up into shorter distances. And at each of these points, you have a source of these entangled photons. And it's between these nearer nodes that you make a communication link. Now, the thing about these sources that I haven't mentioned yet is they're probabilistic, which means you don't necessarily know when a pair is going to be produced. It'll happen with a certain probability, but you don't know exactly when. So you need some kind of device to store your photons until all of these nodes are ready. Okay, that's what's represented by the yellow cylinder here. And then at some point, once you have 2 nodes that are ready, you can then take these 2 photons between these 2 nodes, and you can perform a measurement on them. So you can measure them, and actually by checking whether they're entangled, you can entangle the other 2 photons of the pairs. So now these 2 are entangled. This is called entanglement swapping. And you can do this over the entire length until eventually you're left with just 2 photons that are now entangled. And that's what we call a quantum repeater. That's what lets you go over long distance. So what's the status on that? Where are we? Are we able to do long distance QKD yet? Well, in a sense, yes. So last year, a group in China showed satellite to ground quantum key distribution. And this is quite long distance. This is their experimental setup. It's kind of nice to have an experimental setup that includes a satellite and a telescope. But yes, that's actually what they did. So what they did is they sent information from the telescope to the satellite and back. And this distance is 1,200 kilometers. Okay, so this was kind of a proof of principle. This is like one of the first demonstrations of this. This is the first demonstration of this. But to make it scalable and make a real quantum network, we also are going to need ground links between telescopes and the computers that we want to connect. So that involves using a quantum memory. So quantum memories, you can think of them as converting your information from a flying photon that's going at the speed of light to something that's stationary and stays in place until you're ready. And so that stationary thing has to be something that can store a superposition. It can also be in a superposition. Atoms fill that bill, so a lot of groups work on storing photons in atoms. So the way this works is, the atoms have a nucleus, they have electrons that orbit around the nucleus. And when light hits an atom, it can excite the electron to a higher orbital, so a higher excited state. And then within the lifetime, so there's some lifetime of the atom, it can de-excite and re-emit your photon. So you can see photon in, stored, photon out. That's the basic idea of a quantum memory. And you can do this many ways. One way is to just have a bunch of atoms in a glass cell and send your photon in there, and together with a laser pulse, you can control very carefully how the photon is stored and how it's retrieved. And the key thing is that you can store and retrieve things in superposition, so you can retain the entanglement of the photon. This is a picture of the quantum memory that I worked on as a postdoc. These are 1-inch lenses. This is a vapor cell that has the atoms inside of it. And we have various optics that allow us to control the properties of the light that we store and how we store it. And actually, this kind of level is where we're at still today. So if you ask groups to show you their quantum memory, they'll take you to a large room with big optics tables and lots of stuff on them. So we have a long way to go before we can bring this on chip as well. Okay, so I've showed you kind of how we create photons, how they're useful for communication. Let me just end with one more application, and that is in astronomy. So currently, what limits telescope resolution? What limits the size of objects that we can see in space? It turns out it's quantum mechanics. So the Heisenberg uncertainty principle says that the angular resolution of a telescope, that is, how small an object we can see with our telescope, is limited by this ratio, where this is the wavelength of light that we're detecting, and d is the size of the lens that we're using to collect the light. So to get to better and better resolution, we want a larger and larger lens, larger and larger mirrors to collect the photons. Now, to show how that works, I'm going to show you as we change the lens size what happens to our resolution. Actually, I think this one works right here. No. Okay, I will just play it from here. Okay, so now we have photons that are arriving from two distant celestial objects, and those photons are represented by these rays coming in here. Then we have a lens that's going to make an image that we want to look at to understand what we're seeing. And you can see in this case we're starting with two objects that are separated a little bit, and you can see that separation here. The lens is large enough to see that there are two distinct peaks there. But as we decrease the size of our lens, watch what happens. Okay, so now we've gotten to the point where we can't resolve really what's going on here. If we didn't know anything about the light coming in, we wouldn't be able to say really what we're seeing. It's too blurry. So to improve our resolution, our ability to distinguish objects, we need to go to larger sizes. And one way to do that is to use actually an array of detectors. And in this case, the effective size becomes the separation of the individual collectors. The problem is that, to get this to work, you actually have to send the photon that you detect in one collector over to another collector via fiber optic link. And again, fiber optic links aren't perfect. You have some loss. And so actually the distance by which you can separate these and improve your resolution is limited by loss in the connecting links between these. So here's an image of the way it's done with an array. You have one receiver here, another receiver there. They're detecting photons from the sky, and then in order to get the information at a higher resolution, they have to share those photons. But that means you have to send them over some kind of fiber optic link. Now, the idea for improving with entanglement is the concept of quantum teleportation, which says you can send information about a photon without actually moving that photon at all. That's what's shown on the right here. We have some shared entanglement between receiver L and receiver R. That means they have photons that are entangled with each other, one at R, one at L. And now when they receive a photon from space, all they need to do is make a measurement of a combination of that photon that came from space and the one that's entangled with the other one, and they'll entangle the photon that came from space with the person over here. The detector over here. The detector over here can then have the information about the properties of the photon without that photon actually having to travel through the transmission link. So it's essentially lossless. So this is one way to increase the distance between the receivers without worrying about loss anymore and improving our resolution. So if you're out in space, you're looking back at some planet, using our standard technique, you might have 1 micron wavelength, 100-meter diameter focusing device, whether it's a ray. And then this gives you this kind of resolution, 10 to the minus 8. But with quantum, you can go to 10 to the minus 11. So a factor of 1,000 times better, and that gives you the image in much higher resolution. So so where are we today in terms of this teleportation that I mentioned? Well, experimental teleportation was first demonstrated in 1997, and it quickly improved. In 2004, they showed quantum teleportation across the Danube River in Vienna. So you can actually see here the experimental setup. And so banks can now transfer this, transfer information about a photon without actually sending the photon across the channel. Since then, we've made many more demonstrations, teleportation of entanglement, energy states of ions or atoms, more than 1 qubit of information, 2 qubits of information, and also using that ground to satellite link, teleportation from the ground to a satellite. Of course, I know some of you might be thinking, yeah, there's quantum teleportation like you just described, and then there's quantum teleportation. So let's talk about that. So for this, I'm going to quote Anton Zeilinger, who actually did that experiment under the Danube River. And he's a philosophical person, very interesting, leading physicist in this field. You can find a lot of interesting words from him on various sites. But someone asked him this question, what about teleporting humans? This is all what we want to know. Well, he says there are two major differences. First, we transfer properties, not matter. So what does that mean? That means to teleport someone, you would take all of that person's properties and move them onto another person. That means you would produce someone who has no hair color, no eye color, nothing, someone without qualities. So that sounds a bit unethical, kind of crazy. But in addition to that, they'd have to be in vacuum, and that's never a good thing for humans. So there's that. Also, the fact that atoms in a human being would require 1,000 billion bits to transmit. And even with today's top technology, he estimates 30 billion years to transfer this massive data with our current technology. So that's twice the age of the universe. So we'll need a number of major breakthroughs, to say the least. But he is kind of optimistic. Perhaps in 1,000 years, we'll really be able to teleport a coffee cup. But beware, even the tiniest interference can mean that the cup arrives without its handle. And this method of transport would be far too dangerous for humans, so you wouldn't want to be the first one to try that. Despite all of this, there's major investment going on throughout the world in this type of technology. So in the US, we have this realizing the potential of quantum information science, and there's a lot of funding coming in for this type of research. Also in the European Union, they've launched a $1 billion quantum technologies flagship that allows them to enhance the research towards a quantum internet. And of course, China has substantial investment as represented by their first demonstration of ground-to-satellite quantum communication. And we're part of that. Here at UIUC, NSF invested in quantum technologies for secure communication, supporting groups here. And that includes the first person to show polarization entanglement in those circular things. Does anyone remember his name? Right. I heard Paul. So Paul Kwiat, yay. So yeah, together with him and other researchers throughout the US, we're also working on getting us to a quantum internet. Okay, and Paul Kwiat, I have to mention, have you been to his lab escape? It's really fun. I've done it. And if you use this coupon code, you get a 20% discount. All right, so I'll just end by saying that all this investment has some implications for future jobs. Quantum mechanics, people who understand and do quantum mechanics are in demand. It's a field that you can study and you can get a job at Google, you can get a job at Microsoft. Companies are investing in it. And so, yeah, this is kind of jobs of the future. And thank you so much for your attention.
We have time for questions?
Yeah.
Why doesn't transfer of information by entanglement violate the speed of sound?
Okay, so the thing is that even though the person that made the measurement over here knows what state they got and that means that person over there got a certain state, that information isn't carried over to that person over there. So the information still obeys the speed of light. So that person over here needs to call them and say, I got A, and that person says, oh, that means I got A. You know, that information hasn't been carried faster than the speed of light. Yeah. You want to call? Okay, yeah.
Yeah,
It seems like the problem is that we talk about one of the photons actually affecting the other photon.
Yeah.
It doesn't. You don't have the choice to do like a semaphore and apply information from one side to the other. You don't have control over what photon you measure. When you measure the photon, you get a number, plus or minus 1.
Yes.
And then the other one is the other polarity.
Uh-huh.
Because they have been already connected by this entanglement process,
Right.
which is conservation of angular momentum,
Yes.
for instance.
Right. Yes. Yeah. Ah, yeah.
Could you use the idea of like entanglement for like if you want like have satellites like a satellite in outer space communicate with like very quickly?
More quickly? Is that?
Could you use that idea to like have a satellite in outer space?
Yeah.
Carry the information back to Earth?
Oh, yes. Yes, so that's what they showed with quantum teleportation from the satellite to the telescope. So yeah, definitely. Yes.
You said something about the data being encrypted. How would it be encrypted?
How is the data encrypted? So you mean in quantum information?
Yes.
So the data is encrypted. So the process that I showed you where they have these pairs of photons and they choose a measurement method randomly, that generates a series of bits. You can think of them as vertical, horizontal, or zeros and ones. So zeros and ones, they have a string of them. They're random because when you make the measurement, the photon can either go into vertical or horizontal. And so now you have a series of random numbers, random bits. And now if there's no eavesdropper, you select a subset of those. And if you determine that they agree, then you use the rest of them that are secret still, that you haven't told each other, to encrypt the information in the same way that you would do with a key that's created from two large numbers. Yeah. Yeah. Yes.
Hi. Sorry.
Yeah.
You say that the quantum encryption is completely secure, and I'm wondering to what extent that's theory dependent. I mean, you talked a little bit about the confusion at the very basis of quantum mechanics.
Yeah.
You alluded to the role of the observer and that sort of thing.
Yeah.
So I guess I'd say, like very top researchers in the field, would they be willing to bet, I don't know, the security of the country, future of humanity, something big like that, on the fact that that there is no sort of theoretical backdoor due to the lack of a good understanding of the basics of quantum mechanics?
Yeah, so there are theorists whose career is based around figuring out those issues. I think maybe the discrepancy between gravity and quantum mechanics and resolving that might open up new things, but that's a hard enough problem that people are betting billions on this technology. Yeah.
Any more questions?
There's something? Yeah.
It seems like this is all based on the state of entanglement. I've read that that's rather finicky, so how long can you maintain the state of entanglement before it degrades?
So how long can you maintain the state of entanglement before it degrades? So that kind of comes to the question of the quantum memory that we use to store photons. It also comes to whether the transmission line supports photons for a long enough distance. And so let me talk about both of those. For the storage time, yes, it's limited. Actually, that's the hard part right now. People have shown seconds worth of storage, but not necessarily with all of the other right properties. Like it stores the right color photon, it stores with a high efficiency of storage and retrieval. All of these are hurdles that still need to be overcome. But seconds has been shown up to minutes. So that storage time is enough for a quantum repeater. It's just that other aspects of the quantum memories aren't up to par yet to make them feasible. Now, in terms of just sending a photon, how long does its entanglement last? Well, that depends on what degree of freedom the photon's entangled in and how that couples with the environment. So if you send it over a fiber, you might have, the polarization will scramble. And so that's part of what determines how long you can go. Right now, we're actually limited by physically the photon is lost. It's absorbed, it's emitted into the environment. It's no longer traveling through the optical fiber. Yeah.
Okay, one last question.
Is there a way to tell if a photon is no longer entangled without communicating with the other person?
No longer entangled without communicating with the other. So is there a way to tell a photon is no longer entangled without communicating with the other person? I guess the answer is that in this communication protocol, it relies on you comparing notes at the end. So, I mean, in the lab, you usually have access to all the information, so you can figure that out. But in a communication link, you really rely on comparison at the end. Mm-hmm.
Okay, let's thank
Yeah.
Dana again.